welcome to the Trustworthy Machine Learning course. A few announcements. There will be a co-working session with Evgeny later today. And exercise 2 is now due in a week until next Sunday, coming Sunday. And there was a kind of a request from the university saying students from this course should participate more in the survey that's running within university now. I guess you also have other options to give feedback through the other Google Form surveys, so probably that's why you don't do it. I think it's fine if you don't do it either, but they say there's some internal threshold for this survey, 20% of participants. So yeah, I don't know what happens if that's not met, but please do it just in case. So we can resume the training data attribution. Okay. Let's talk a little bit about evaluation. We wish to do some counterfactual reasoning over training data. So we have a specific test sample of interest, and we wish to know what's going to happen to the loss value for this test sample when you remove certain training samples. So if you have the original data set like this, the loss is 0.312, and if you remove one sample from the training set, the loss will be 0.308. So there is a 0.004 difference here, which is caused by the removal of this training sample. Of course, one can do full retraining to find out the difference in loss value, but that's going to be very expensive. So you do a lot of approximations to make sure that this is not super impractical, right? So what's important here is to kind of also measure the efficiency of your approximation algorithm. So instead of doing the full training, retraining, how much time you are saving by doing some approximation. So efficiency and soundness are important. So efficiency computation is, for example, done by wall clock time measurement. So there are now different ways of measuring sample-wise contribution from the training set. And you see on the right column, they measure the number of seconds for each method. So that's what you can do. Or you can turn to more theoretical kind of ways of doing it by looking at the big O notation of how much time it takes for each method to compute. Yeah. Just showing these are some examples of possibilities. And for this course, we should focus more on the soundness evaluation. So, you know, there's a very definite target for training data attribution, which is the change in the loss value for this test sample before and after removing a training sample. So we have a very specific target to approximate, which is the difference in loss value. And what we are doing is we are measuring the approximation. And so we can do some kind of correlation plot here, where the x-axis is the actual ground truth, the change of loss value after retraining, and y-axis is yeah, the other way around. So y-axis is the ground truth, and x-axis is the approximation. It doesn't matter actually. And here the interest is whether these two sets of values are following closely to each other, right? So in other words, you wish to achieve very close to x equals to y line in this plot. So one could measure, for example, Spearman correlation or Pearson correlation. If you strictly believe that they should be equal, then you can measure Pearson correlation to see if they're linear at all. If you only care about the rankings, the correct ordering of samples according to the influence, then you can also measure Spearman correlation, which is Spearman correlation is basically Pearson correlation on the rank index. Okay. And now, one question is whether leave on out objective here is a suitable target. There are many methods based on this assumption that people will love to find out what's going to be the impact of removing this training sample on a particular test sample. But we are not entirely sure about that, and that's why this is one of the papers that's actually going to be presented next week at NeurIPS. So we looked into the level of noise actually in this target, because if you think about removing one sample from, let's say, millions of training samples, is that going to have that much influence on the test sample, right? And it turns out DNN training is also contains a lot of randomness as well. So here the real question is whether the impact of removing this one sample is bigger than random noise due to training. So there is random initialization, or the ordering of batches or sampling of batches due to stochastic gradient descent. So are these random sources introducing more changes into the loss value compared to removal of one sample? So that's why we came up with this kind of diagram where we illustrate the fact that if you train with this data set, you eventually end up with some kind of distribution over the parameter space instead of a single point. And of course, according to different distributions of parameters, you're also going to have a distribution of test loss on the test sample of interest, right? So looking at the counterfactual is basically comparing these two distributions, or the other way to say that is you look at the difference of these distributions, and that's going to look like some 1D distribution over real space. And your question is whether that random variable is meaningfully above 0 or below 0, right? And it turns out, according to our experiments, in many cases, so we looked at the p-value of hypothesis testing. So we treat LOO value as a t-distribution, student t-distribution, and then did the hypothesis testing with the null hypothesis of mu equals to 0, meaning that removing zj has no impact on the test sample of interest. And to kind of see the significance of removal, we can look at the p-value for statistical significance. And it turns out, so these are p-values for different data sets and different sources of randomness. And if you consider all randomness, it turns out the signal to noise ratio is very low, meaning that the randomness is contributing much more to the shift in loss value than removing a sample. So that kind of shows how fragile the objective could be for removing a single sample. So a lot of other people try to look into different possibilities. So perhaps if you remove multiple samples, the impact is much more statistically significant, perhaps, right? Because this is the central limit theorem, right? If you average out all the influences of individual samples, then the variance goes down, right, with the rate of square root of n. So in other words, it's always better to kind of select multiple samples to remove. And yeah, for example, let's say you remove half of the samples from your training set. The impact of that will be much more significant than, for example, changing the random seed for training the network. So people do leave many out results as well. So they first rank all the training samples according to predicted influence and remove these samples one by one. So on the x-axis, you see the number of data points removed in log scale. So you are removing 1 sample, 10 sample, and then 100 samples according to the dictated influence ranking. And see how much the test loss value changes as you go. This influence functions, this kind of training data attribution gives you also indication of whether removing this sample will improve the prediction or decrease the prediction correctness. So there's a sign as well. So for the blue cases, you're actually removing helpful training samples that are expected to increase the so removing helpful sample is not a good thing, right? So removing them will increase the loss value for the test case. And removing harmful samples will decrease the loss for the test sample. And as expected, we see roughly the predicted trend, right? So removing helpful samples increases the loss value, while vice versa. So we can do this kind of experiment evaluation as well. Leave many out. It's kind of similar to remove and predict. Remove and predict evaluation for feature attribution, right? You remove pixels and then see how much drop in performance you see. Or you can do some kind of correlation analysis as well. So instead of looking at the influences of removing single samples, you can take a look at multiple possible removal of groups of samples. So each point here is a result when you remove a subset of samples from a training set. On the y-axis, you see the actual model output changes, like loss changes. On the x-axis, you see the predicted loss change. So x-axis is your method, and y is your ground truth. And if we see a very close correlation between the two, then we say, yeah, our method is actually approximating the group-wise attribution good. Okay. So these are for soundness, and now we can take a look at end-to-end usefulness of TDA, training data attribution. Why do people use potentially training data attribution? First, because they wish to do some debugging, right? They see that they believe that perhaps there's some mislabeled samples, and they wish to kind of find out which ones are erroneous, and should involve more annotators doing the redo the annotation for these samples, for example. Or you have some specific failure cases, like the self-driving car is running into some people, right? And you wish to fix this behavior. And to fix this behavior, which training samples they need to redo the annotation or reintroduce. The other aspect of this potential use case is legal and trustworthiness aspects of generative models. So a lot of people nowadays use DALL-E or ChatGPT for generating content. So there are typically 3 issues here. So one is hallucination problem, right? Is it speaking the truth? 2 is whether it's using copyrighted material. 3 is whether the generated sample contains some private information, like card number, credit card number from someone else, or someone else's phone number, and so on, right? To tell if the model is making use of these information, they're eventually coming from the training set, right? So it's very useful to be able to tell whether from which training sample this generated sample is coming from. is rooted on. So because of that, I'm kind of excited about the possibilities from training data attribution these days. There are very good connections between training data attribution and foundation models, generative models. So here's one example of possible way to measure end-to-end usefulness of training data attribution. You can try to do some mislabeled training data detection. How can you do mislabeled training data detection with the training data attribution? For that, we introduced the notion of self-attribution here. Self-attribution means you're trying to see the impact of removing a training sample, a sample from the training set on the very training set itself, training sample itself. So there's ZJ, right? ZJ training sample. You remove it. Well, first of all, you train the whole model and then you measure the loss on that training sample. And then now you remove this training sample and measure the loss of the model on this particular training sample, which is not now not part of the training set anymore, right? So why do you care about that, right? Because let's say there are two cases. If ZJ is sort of unique, then removing this sample will seriously undermine the capability of the model to do well on this sample because there's no replacement around it. So if ZJ is kind of unique and outlier or out of distribution, then removing this will increase the loss value significantly on this particular sample. In other words, that's going to have a high self-attribution score. But on the other hand, if that sample was very similar to surrounding samples, let's say, there are many similar samples and in the training set, then removing this sample will not make so much difference on the for the performance of the model on this particular sample because there are so many replacements. So that means there will be very low self-attribution score for this sample. And if you think about mislabeled samples, our assumption is that annotators typically do not make massive amount of mistakes. They are paid, they are supposed to be doing good, right? Doing well on this job. So mislabels are supposed to be very rare. And therefore, these mislabeled samples are typically the ones that are outliers and very special cases. And so removing this sample will seriously undermine the performance of the model on this mislabeled sample. Okay, there's a dog image and then someone labeled it as cat, right? If the model is kind of trained on this sample, the model will try to memorize this sample because that's so different from the other samples. And so removing this sample will seriously undermine the, well, it will remove the possibility of model to memorize this sample. So there will be a huge self-attribution score for this sample. So we can use this property to detect mislabeled samples in the training set. And if this is the task, you can also do some kind of detection evaluation like this one. So on the x-axis, you count the number of samples that are removed or that are kind of considered. On the y-axis, you have fractions of mislabeled samples identified. So you have sort of recall rate on the y-axis. On the axis, you have you're sliding through all training samples. You can also do some kind of average precision metric here as well. Like in this table. So you can try to measure the area under curve or average precision to measure the detection capabilities. Yeah, and here's efficiency measurements as well. Yeah, so far no questions. Can I move on? Okay. So let's talk about intrinsic interpretability. So for feature attribution, we looked into sparse linear models or um, shallow decision trees, for example. These are examples of intrinsically interpretable models, right? So what are the analogous interpretability by design for training data attribution? Okay. I would say non-parametric models are intrinsically interpretable from training data attribution perspective. What do I mean by non-parametric models? It means there are no parameters in between. So, well, typical machine learning involves some parameters. So you kind of compress your training data into a set of parameters and use only these parameters for making the prediction for a test case. But for non-parametric models, for a particular test case, you look back into the training samples, search for something similar in the training samples, and then based on the patterns found from these particular training samples, you make the final prediction. So it's sort of a lazy way of lazy implementation of machine learning. You don't do any computation until you are given a test sample. And if it's given, then you go back to training samples and look for similar cases. And then based on that, you make the prediction. So what are examples of non-parametric models that are potentially supporting this training data attribution by design? Classification and regression. So for classification, you have k-nearest neighbor. Regression, you have kernel regression, for example. So what is a KNN classifier? You first need some embedding functions. So for every training sample, you're going to embed them into some embedding space. Could be a Euclidean space. And given test sample, you're going to apply the same embedding function like a neural network to map this into the same space. And then you measure the distance between this test sample against all the training samples and see what are the k nearest neighbors for this test sample. So let's say if k is 3, like here, then you're going to have this red star and two green triangles corresponding to each class. And then what you're going to do is you're going to do majority voting. So when case 3, the majority is actually green, so your class will be B, the green class. When case 7, in this case, the majority is actually red again, so your class prediction will be A. You do something like this. So the point here is that if you do something like this, then you know exactly based on which samples you're making the prediction. So you have a ground truth counterfactual question. So for example, let's say you remove one of the green samples here, and you know right away what's going to be the prediction for this yellow question mark, right? So you can very efficiently answer counterfactual questions in this case. It's sound because there's no approximation whatsoever here. When k is small enough, then it's selective, I would say. Of course, when k is the entire data set, then you're not selective anymore, but also that's not very useful from machine learning perspective either. So yeah. Now let's go quickly over the regression cases as well. The story is the same. So you have kernel regression here, for example, with the k nearest neighbor kernel. So given a test case, there's x-axis and there's y-axis. And the blue dots are training samples. And let's say a test input is 2.1 or something here, right? And then to make the prediction for this 2.1, what you're going to do is you're going to look into 16 nearest neighbors on the x-axis. These are red points here from the training set, and take the average of the outputs for these samples. And that's exactly going to be your prediction for that test sample. Yeah, so here the only difference is that you're taking average of the outputs. But what is perhaps more popular in kernel regression is using Gaussian kernel. You can also write down the equation in a neat format here. So for a test sample X, your prediction will be based on the outputs of individual training samples, where you're going to put more weights on the training samples that are closer to X. So K sigma of X and Xj is kind of measuring the similarity between X and Xj. So if they're close together, then you give more weights, and vice versa. Actually, you're preferring closer solutions quite a bit because this is an RBF kernel, so the tail is super exponential, so like this. So again, you can do some kind of threshold over kernel and say when the kernel value is less than 0.1, for example, then you do not consider them as kind of having any influence on the current prediction. And so you can do easily counterfactual reasoning here as well, very efficiently. You can just search for similar samples in the space. And of course, here you can do embeddings rather than raw feature values here as well. So if X is image, for example, then you can put some kind of neural network on top of this to map X onto some high-dimensional embedding space, and then do the kernel regression on top of that here as well. Yeah, so it's counterfactual, sound, selective, and efficient. Selective if sigma is small enough, right? So so you see the impact of sigma here. So sigma is controlling the size of neighborhood that you're going to consider. So if sigma is small, like 0.5, then you're only going to base your prediction on very small neighborhood. But if you do greater values of sigma, then you're smoothing it much more because you're not considering a bigger window. But of course, if you do it too extremely, then you have too less complexity, I would say. And you're also considering way too many supporting samples. Okay, so these are so far interpretable functions by design. Let's take a look at training data attribution, unless there's some remaining question. Okay. So now we looked into, interpretable by design cases, but what about neural networks? Neural networks are not interpretable by design, of course, for two major reasons. So one is because it's parametric, of course, and the dependence of the prediction on the parameters is nonlinear, of course. But we are not just happy with attributing to parameters themselves, but we wish to go all the way back to training data. So it's a nested function, right? So from training data, there's parameter, and then there's a final prediction on this test case. So you can sort of apply some kind of chain rule here, but if you look at individual functions here, parameter to final prediction is nonlinear. Training data to parameter is also nonlinear. It's not only nonlinear, but also it's multi-valued, right? Because with the same training data, there's no guarantee that you're always going to end up with a single parameter. So it's a very complex problem. And when you have a complex problem, your strategy is to simplify the problem. So the first strategy is to make some simplifying assumptions to make the solution unique given some training data. The way you can, I'm going to talk about how to do that. The second solution is to take the derivative of the test prediction with respect to each training data with the parameter in the middle. But now this parameter is a optimal solution for some optimization problem. In that case, you have to use some kind of implicit function theorem to be able to differentiate through the solution. But this is non-examinable. Okay, so how to make the solution unique? You can say your loss function is strictly convex and smooth. And then, of course, then there's only a single solution for the loss function. Yeah, and then I'm going to go into details of how to derive. So basically, I'm going to do some chain rule to take the derivative of the final prediction on individual training data. And for that, I'm going to use implicit function theorem and chain rule, but the exact details will be non-examinable. But I wish to kind of give you a sketch of how to do the computation here. So for that, I'd like to introduce some terminologies here. So eventually the question is, you wish to see the impact of removing some training sample on some test sample, right? I'm always going to write Z for the tuple of X and Y. And there's always a subscript for training samples, no subscript for test samples. This is going to be the test loss. This is going to be the training loss, empirical risk minimization. And I'm going to write down the solutions. So there is only a unique solution in this case, right? So theta hat is the unique solution for the problem given by the original training set. Whereas I'm going to write down theta hat minus j for the optimal solution for the training set, except for zj, the training set of interest, training sample of interest. And I'm interested in the difference between lj theta minus j, lz theta minus j minus lz theta. This, so did I? Yeah. So I'm going to introduce this some general notion of removal. So removing is a discrete action, right? And so it's sort of impossible to differentiate, make a derivative of this action. But of course, you can do some generalization in a smooth way by introducing this this epsilon here. So you have the original loss value here plus epsilon times the loss value for zj. And you note that if epsilon is minus 1 over n, then it's exactly removing this loss value from the loss formulation. So this is a continuous notion of removal. And I'm going to write down the optimal solution in this case as theta hat epsilon j. And from that, we wish to prove this equality here, saying that if you differentiate this optimal parameter for this modified loss value with respect to epsilon, then at epsilon equals to 0, the gradient is exactly minus Hessian inversed times this vector, the gradient of L with respect to parameters at optimal parameter at the training sample of interest, Zj. Okay, and Hessian is defined as an average of the Hessians at every training point. Or you can think of this as a kind of average loss, and then you take the Hessian of that, because this is anyways linear. Yeah, you can put this delta squared all the way outside as well. So then you're basically taking the Hessian of the empirical risk. Okay, so I'm going to prove that, but with a sketch. So this is non-examinable again. So let's start with the definitions. So theta hat is exactly the optimal solution for the original, and theta hat epsilon j is the optimal solution for this modified loss. Because these are optimal solutions, and also L is smooth and convex, we have the necessary conditions for optimality, meaning that the gradient at the optimal solution should be 0. So we have ingredient 1 here, which dictates that if you take the average over the individual loss values, that should be 0. Likewise for the second loss formulation, if you take the average and then do this as well, then your loss value should be 0. Sorry, gradient should be 0. These are ingredients 1 and 2. There's another ingredient here due to implicit function theorem, saying that this theta hat epsilon j is differentiable actually with respect to epsilon at epsilon equals to 0. If you say something is differentiable, then you can also expand it through Taylor expansion. So you can basically write it down as epsilon. So theta hat, where epsilon is 0, which is exactly theta hat, and then plus epsilon times the gradient at epsilon 0. And then everything else is basically literal of epsilon. So with these 3 ingredients, we can do some computations here. So the aim is to now write down the gradient of L, the parameter gradient of L at theta hat epsilon j in terms of this original gradient. So we can plug in the ingredient 3 inside this theta hat epsilon j, and then what we're going to have is theta hat plus epsilon times gradient plus literal or of epsilon. And then you can do another Taylor expansion because L is indeed differentiable. In particular, the gradient of L is differentiable because L is twice differentiable. And so we can write down gradient of L plus the twice gradient of L here times the gradient of theta hat epsilon j. And everything else is still bounded by literal of epsilon. So this is the formulation that we got. And then we plug this into ingredient 2, which is dictating the necessary condition for the optimality for modified gradient. So we plug this into ingredient 2. If you remember, ingredient 2, it's here. So we can basically replace this one with the one that we got now. So yeah, if you do that, then if you trust me, then you get something like this. And now, using the first ingredient, we actually cancel out the first term, right? Due to optimality, this is actually 0, fortunately. And then we end up with some terms here. We can remove epsilon everywhere because epsilon is put in front of everything, okay? And we're going to end up with, this kind of formulation where H is the Hessian again, which is basically replacing this expression here. That's it. So eventually we have, if you divide through by epsilon, then we have this and this term summed together should be 0. And if you, so eventually we were interested in this quantity. So we're going to send this to the right-hand side and then multiply each side with Hessian inverse. Yeah, and then we're going to end up with this kind of formulation here. But now, okay, I wish to kind of write it down here. So you see that this is now minus Hessian inverse times this vector here, right? Okay, keeping that in mind, we can do further computation now, because our interest is not just taking the derivative of the optimal solution for this modified loss value, but we wish to look at the influence of removing Zj on the test sample Z. So how is that computed? So we define that value as the derivative of L with respect to epsilon at this modified optimum, because like this value is exactly approximating the difference between the loss value, including the zj, and loss value excluding zj, right? Because that's the rate of change at the removal of zj. And we can apply chain rule here. So we first take the derivative with respect to L, and then take the derivative of with respect to theta, and then take the derivative of theta with respect to epsilon. Okay, that's chain rule. And using the lemma before, we can replace this derivative with Hessian inverse times the parameter gradient. So this is the final formulation that we get for influence functions. So if you go to the original paper, you're going to see that this is the equation for influence functions. So let's now take a look at what this influence function is doing. I would say it's a dot product. It's basically a dot product between two vectors, where one vector is a parameter gradient for test sample, and the other vector is the parameter gradient for the training sample. To show that that is the case, I'm kind of doing diagonalization of the Hessian matrix. If you've been to a linear algebra course, if a matrix is metric, then it has all sort of nice properties, like you can diagonalize it first of all, and the matrix that's inducing the diagonalization, the change of basis, is basically orthonormal vectors. So you do kind of rigid rotations of the space to diagonalize the Hessian, and you're going to have a diagonal here dictating the eigenvalues, where each eigenvalue is telling you how much curvature you have in different directions of your original function. So the way I see Hessian is it's basically a quadratic function where the curvatures are kind of aligned in orthogonal basis vectors. If you remember that the function is actually strictly convex, we should have positive definite matrix, meaning that the eigenvalues are positive. Because if it's 0 or negative, then you're going to have some directions where the function is going down as well. And then that's not a convex function, right? So you should have all the, at the optimal point, the Hessian is dictating kind of positive curvature on all directions. Okay. And you can diagonalize H into Q transpose lambda Q. In this case, you can easily do inverse of Hessian, which is basically, you take the inverse of lambda only, which means you're basically doing the reciprocal along the diagonals of this diagonal matrix. And you can also write down this influence function in a different way. So we realize that Q is here, and then lambda will be here, lambda inverse will be here, and then Q will be here. So eventually you're taking the dot product between Q times gradient and Q times gradient, where there's some kind of modulation of scales along different axes. So first dimension will be modulated by the first eigenvalue, inverse, and so on. So what does that tell us? So I would say this is a generalized dot product between two parameter gradients. And you do put less weight along the direction where the curvature is greater. So when the function is very sharp along some direction, then you do not consider this direction too much, right? Yeah, that's sort of the geometric intuition of what influence function is doing. Yeah. So if you're taking dot product, right? What dot product measures is some kind of similarity measurement. So in other words, if the influence is great, what that means is the parameter gradient for that test sample is very similar to the parameter gradient for some training sample. Okay, that makes intuitive sense because let's say you have some impact of some training sample on the parameters, which is given by the parameter gradient. And let's say you have seen new test sample, but that's having kind of a very similar impact on the parameters with a very similar kind of input parameter gradient. That means that sample has kind of similar impact, and so removing this training sample will perhaps have a bigger impact on this test sample. Okay. So it's kind of measuring similarity, but from the perspective of how it's going to impact the current model in the current iteration after optimal point. Okay, I wish to talk about computational complexity here, but after 5 minutes break. Okay, so influence functions are expensive. If you look at the dimensionality here, it's huge. So the involved number of parameters is from millions to billions, depending on which model you're using. The training data, also for practical applications, it's typically millions to billions. Well, millions in many cases, billions for foundation models, I would say. So the gradients here are actually p-dimensional vectors, which is huge. And the Hessian is p by p matrix, which is alone quite huge, but also this is after averaging over n training points. So that's very expensive. And also, if you want to do inverse Hessian computation, then first you have to build a Hessian matrix, which takes n times p squared operations. And if you want to take the inverse, that's p cubed operations in big O notation. So that's very expensive. So we talk about how to speed this up through some approximation. It's called LISA algorithm, linear, I forgot the full name, but this is like linear kind of approximation or something. LISA uses some iterative approximation to ease the computation here. Because I don't want to always write down this gradient all the time, I'm going to simplify with V. And so I can write down the Hessian inverse times V as Hessian inverse V, basically H inverse V. By the way, you notice that I'm putting Z here instead of ZJ. So it used to be ZJ here, but you know, like you can always swap these two, right? If you take the transpose of everything, then you have Zj here as well, and it's the same thing because eventually this is scalar. Anyways, so now it's H inverse V. The problem of approximating this, okay? And once you have this, what you can do is so this is a vector, right? So we can take the dot product between this vector and the other side of the gradient, right? And that's how you compute the influence values. So you're gonna compute this for a single test value. It's one-time cost, and then I'm gonna take the dot product between that and all the individual training data. Okay. So what are the ingredients here? So first observation is that you can write down the inverse of a matrix as a geometric sum, right? As long as A is invertible and its eigenvalues are all bounded by 1. And also I'm going to do some stochastic approximation of the sum here as in SGD. So there's a parallel in scalar case. So when R is a scalar which is bounded by 1 in absolute values, or in complex plane a disk with 1, and if R is not 0, then you can also write down the geometric sum as 1 over 1 minus R, right? This is basic. And if you rearrange a lot of things here, then you get R2 minus 1 is geometric sum of 1 minus R. The same actually applies for an invertible matrix with eigenvalues smaller than 1. So this 1 minus h to power of I summed over t, this approaches to h inverse as t goes to infinity. And if you multiply v as well, yeah, the same is true. So using this property, instead of inverting a matrix, I'm gonna use the geometric sum to compute this approximately. So I'm going to define Wt based on this partial summation. So the intuition is for large enough t, this will be close enough to h inverse times v. And one exercise here is to show this equation here. Wt is actually equal to v plus 1 minus h times the previous iteration Wt minus 1. So with this recursive formula, you can repeat this several times to eventually compute an approximation, where W0 is actually starting from just v, okay? And if you remember that Hessian is an average over all the training data, because now we have iterative formulation, we don't have to kind of use all training samples at each iteration, but we can just use one sample per iteration, as in SGD. In SGD, we are not taking the gradient with respect to all training data, but only a partial sum of them, right? In this case, you can think of this as a batch size 1 SGD. So instead of a full summation, I'm just taking one Hessian on one training sample at a time, at random, right? And if t is great, then you're basically considering a lot of Hessian values here. So eventually, maybe Wt is still a good approximation of the original Hessian inverse product. So this is the algorithm, right, for doing the least step. But of course, we made two assumptions here: invertibility and eigenvalues bounded by 1. So these are, yeah, critical assumptions, so you cannot go around it. But at the same time, these are, I would say, there are tricks to make any arbitrary matrix to satisfy these two conditions. But one good thing here is that L is strictly convex and smooth in the first place, so H is supposed to be positive definite. And so you don't actually have to worry too much about the first condition because H should be invertible in that case. But the eigenvalues are probably not bounded, so yeah, there should be something done. But actually, in general, for deep neural networks in general, the solution may not be, at the solution point, your Hessian may not be positive definite. Maybe it's flat along some direction, meaning that the curvature there is 0. In that case, you have positive semi-definite matrix, or sometimes even you have not reached any convergence, and so it could be a saddle point, for example, or kind of on a slope or something. It's not even a critical point. In that case, your Hessian matrix will not be invertible at all, right? But eventually, we wish to use this algorithm for general deep neural networks, right? So there should be a way to kind of turn this into a matrix that satisfies the two conditions. And this is a general recipe for making an arbitrary matrix to follow these two conditions. You introduce damping and scaling. So damping means you're adding some diagonal uniform values along the diagonal, right? In particular, you're adding scalar d along all the diagonals of the matrix. And then you have some scale factor to make sure, the h is scale factor that's multiplied in front of h. So there exists some d and s such that this resulting matrix is positive definite and bounded, has bounded eigenvalues below 1. Okay. Now, because this modified h satisfies the convergence criteria, again, the recursive algorithm where you replace the original h with di plus h over s, this recursive formulation will converge to di plus h over s inverse times v, okay? And the good thing here is that typically the damping should be very small. It's greater than 0, but very small, like scale-wise, it's 0.1 or something, right? In that case, the inner part is close enough to h over s, and so if you multiply 1 over s in front of it, you're going to have something very close to h inverse times v. Okay. So what you're going to do is you're first going to turn the matrix into nice form and then multiply 1 over scale at the end. So this is the summarization of the eventual Lees algorithm. We have some damping factor, first of all, and then scale, number of iterations, and training samples, which are corresponding to the number of iterations. So you first initialize V with the gradient, and W is something that, W is basically WT, and for the first iteration you have V for W, and then at each iteration you're going to compute the Hessian on this sampled training sample. And then you're going to do Hessian W product here, divided by scale, and you have some damping function. So this is basically implementing this step here, okay? And then after doing T iterations, large T iterations, you have W, but you're going to scale it down with scale, okay? And eventually that's going to be your H inverse V approximation. I think that's part of the exercise as well. So, any questions so far? Yes.
So the scale and dump, is this a hyperparameter?
Yes. Yeah. So you have to run different iterations and see what are the good values there.
My other question is about the first assumption we made, because it sounds so strong. We made the loss curve convex.
Yeah.
Isn't it? This is a very strong assumption.
It's a very strong assumption, and that's not going to hold in practice at all. So, but still, you need some place to start your theoretical foundation. And well, this is typical in deep learning. You make a lot of strong assumptions to build some theory, and then eventually what you do is you hope that it works in practice. And of course, it doesn't work in practice. And so there are still a lot of research around how to make this more realistic. Eventually, when you measure influence value, you're basically what you are measuring is essentially the influence for a quadratic form around the deep solution, deep learning solution. So you have second order approximation of the local neighborhood of your solution for your deep network. And then you explain this approximation, basically. And yeah, of course, that's very limited, and that's not really explaining the whole space of parameters, right? But still, there's only so much you can do, right? I wish to talk also about a different way of doing training data attribution. So I would say tracking is sort of integrated gradient analog of training data attribution. So influence function is a linearization of the mapping from training data to test prediction or test loss. So the question is whether there's a good analog for integrated gradients here. For that, we look into this, it's called telescope sum, right? You can break down the final loss value for test case into smaller steps. So theta t is the final iteration parameter. So you can start from the initial loss value for z, and then you take the difference between the loss value for this sample between 0th iteration and first iteration and so on. So, so there's a natural notion of the contribution of Zj to this particular test loss given by the summation of this difference in loss value for this sample, where you're only summing over the parameter updates, where the parameter update actually involves Zj, okay? So this is a visualization. So let's say this is the final sample of interest. It's kind of hard to see, but it's a car seat, and then there's a zucchini that's holds to the seat belt, right? The initial loss value for this one is pretty high, right? Zucchini. And then by looking at this sample, actually the loss value for this sample drops to a certain degree. But at this iteration, the model sees this sample, which is labeled as seat belts, right? And because these are kind of similar, now the model makes a small belief that, yeah, this is probably seatbelt rather than zucchini. And the loss goes up here. And further up here, looking at this sample, which is again a seatbelt sample, which is close to this sample. Yeah, you can see the same sample twice, right? By the way, on the way, you're gonna update the contribution of each training sample here for this particular test sample. So far it was 0.3, but now it's another 0.5 is added here. But looking at true zucchini samples, you're also going to decrease the score again, loss value again, and so on, right? So by doing this, you're going to find the training sample-wise influence on this particular test sample. And you're basically adding them up. So that's the idea behind tracking. And the nice thing is that we have recovered the completeness property here again. If you remember that from the integrated gradients. The difference between the loss value eventually for this sample, between that and initialization, that's going to be the sum of the individual attributions along the way. But there's a critical issue, which is that when you update the parameter, we are not updating per training sample. So for example, we are going to have this kind of improvement here, or yeah, improvement here, like this blue arrow here. But eventually this drop in loss is not because of this single sample, but a group of samples in the same batch, right? So how are you going to find the attribution of individual sample in a batch to the loss update? Yeah. So we still have to decompose this into individual samples in the batch. So for that, we look into each parameter update. So theta t is basically theta t minus 1 plus eta, which is learning rate, divided by the batch size times the summation over the batch, where the gradient from individual samples from the batch is added. So we have to identify the contribution of each sample here towards the final loss change, right? So to do that, we compute this L of Z and L theta t plus 1. So we're going to replace the theta t plus 1 by this update formula here. And then again do Taylor expansion because L is perhaps differentiable. And what we have is L of Z theta t plus the internal summation. So because eta is supposed to be very small, and b is supposed to be very large, this is going to be infinitesimal, ideally. So you can take this out, and what remains is the gradient of L, with respect to the second argument here, at the location theta t. So yeah, you have this formulation basically. So the difference between theta t plus 1 and theta t for Z is essentially dictated by this term here, which is the summation over individual samples in the batch. Like this, right? And then there's a natural notion of individual contribution of sample Zj, which is given by, actually there should be a transpose here. So it's a dot product between these two. Yeah, so and this is the case when you have Zj inside batch Bt. If Zj is not part of Bt, then the contribution is naturally 0. So this is the final formulation for track in. So the influence of Zj to Z is the summation over iterations, where you're only going to sum at the iteration when the training sample is included in the batch for that iteration. And you're going to add the dot product between the parameter gradient at Zj and the parameter gradient at Z. And there's a factor of learning rate, eta t here. So you see some kind of similarity between tracking and influence function here. Both are kind of a version of dot product, inner product. For tracking, you're measuring the inner product across all the iterations of training. Influence function is measuring the dot product at the final solution, but according to some distorted inner product measure, according to the curvature of the solution. So looking at this, what comes to my mind is training data attribution is eventually a retrieval task. Given some training test data, we're looking for some training data that are similar to that test data under some metric. What is a retrieval task? Retrieval task is the task where you're given a query and you're required to find a similar set of samples from some training data or some database. And the typical approach there is you define some embedding functions. So you're always going to send all the samples, training samples or test samples into the same embedding space. And in the embedding space, you're going to use some metric like cosine similarity or Euclidean distance to measure the nearest neighbors. And then you're going to do some k nearest neighbor for retrieval. So we can kind of put all these influence function and tracking into the context of retrieval task, where the embedding function is now the parameter gradient. It's always the case, right? For influence function, you are representing each sample as the parameter gradient of the loss for that sample. Tracking as well, but now you're considering multiple intermediate checkpoints at the same time. And you're concatenating these vectors into a huge single vector. And the distance metric for influence function is given by a dot product where Hessian inverse is kind of in between. For tracking, you have also a dot product, but it's a block diagonal matrix in between, where block diagonals are again diagonals of learning rates. Okay. So given this kind of unified formulation, right, this is a typical technique in research. You try to find some unified formulation of existing methods, and based on that, you try to simplify the methods, for example, or try to think of new ways of approaching this problem. If it's a retrieval problem, then can you think of new types of embedding functions and new types of distance metrics, or try to kind of mix and match different solutions, different ingredients from different methods. So that could be an interesting research direction from here. In fact, there has been one work which has claimed that some baseline retrieval methodologies beating influence functions and tracking approaches. So it's called BM25, and this is basically, if you know TF-IDF, BM25 is a similar kind of way to measuring document similarity in the database of documents. It's a handcrafted one. People came up with like different effective hyperparameters to do the similarity scoring. And in practice, it seems to work pretty well. It's basically a function of all these different vectors, including TF, like term frequency, and QTF, which is like term frequency in the query, and so on. And according to this paper called Towards Tracing Factual Knowledge in Language Models Back to the Training Data, they say BM25 is actually beating, for example, tracking. So higher is better here, and it's 77% here, and tracking gives you, less than 50 sometimes. So here the question is whether you really need those dedicated TDA methods at all. They are very expensive. And the other question is whether retrieving methods that exist out there, are they going to solve the problem at all already, maybe? And that leads us to perhaps cheaper and more effective ways to attribute to training data. And also with respect to some end goals, right? So yeah, I feel like there's a lot to explore in this direction, so I wish to do more research in this direction. Okay. No further questions? Yes? Mm-hmm. Yeah, that's a good question. I thought about it as well, and then I realized it's probably hard to express it in terms of metric space, because what you do is like TF-IDF. So you have given a pair of documents, you measure the TF and IDF, right? So you basically have some division fraction where the numerator and the denominator has combination of all these factors. It's really not interpretable actually. And then that's going to right away tell you what's the similarity between two documents. So there's no real embedding space here. I would say it's more like there are features like these ones, and then there are some nonlinear interactions to compute this similarity score. So it's kind of hard to make a vector database, and then from this vector database compute similarity efficiently. But not saying that this is inefficient. This is still very efficient because it doesn't have to go through all these, let's say, transform architecture to extract the features, but you're just counting some words and so on, and that takes that's very quick. So, yep. Okay. So I think one problem with training data attribution is they're too much focused on attributing to single sample. And we should probably attribute to groups of samples. The reason being, right, as I said, the task is kind of stochastic. And so if you're removing a group of samples, the impact is has less noise compared to the noise coming from the training. So the question is whether we are asking a useful question at all. Because also in practice, people do not care too much about the decision to remove a single sample or not, right? They think more about, let's say, introducing a new group of samples that's perhaps going to improve the model for handling these kind of cases, for example, or trying to handle, like, there are some erroneous group of samples, group of test samples that you wish to address, and you wish to make a decision whether to introduce another group of samples to fix them or remove these group of samples because we believe these are not helping the model at all. So the kind of reasoning that we need is group-wise rather than individual sample-wise. And for that, I think it's important to think about more global counterfactuals. So now we consider a group of samples S and try to see what's going to happen if you remove this group of samples. Okay, so yeah, there is a bit of inconsistency here. So I said remove here, and then I said this is the subset of training samples that we are going to use, right? So I'm going to unify the terminology here to mean to indicate the samples to use for training as S, right? So you're going to have some test sample of interest Z, and then your loss of trained model on Z, which is given by L of Z, where I'm going to list all these training samples here. And S is the subset that is used for counterfactual training. And here the question is, what's going to be the counterfactual loss L of Z given S? The answer to this, or an approximation to this, is given by data models. Because, yeah, if you think about computing this value every time you need the value for S, this is very expensive, right? It's even more so than individual training samples because the number of possible subsets is exponential with the number of training samples. So to address this problem, people came up with something called data models, which is doing linear approximation of the original change of loss values or the loss prediction. So the idea is that we are going to assume the loss at sample Z as a sum of individual contributions of each training data point in S. Okay. So in other words, it's beta 0 plus the summation of beta j, where j is the index is included in this subset S. Okay, I'm going to define that as this new function g beta of x. Okay. You can also try to write this down as a linear function of beta 0 and beta transpose 1 s, 1 subscript s, where 1 subscript s is a multi-hot vector, 0, 1 vector indicating which indices are included in S. How do you train beta, or how do you approximate beta? You can use a lasso regression objective. So you have, for example, beta naught plus beta transposed 1 Sn. You're trying to make this value close to the actual loss value on this subset called Sn, right? And there's a regularization of beta because you don't want beta to be activated all the time. So you try to induce some sparsity here. Here, one notable thing is you're going to use multiple subsets of the original training set, S1 up to Sn. And here, you can think of this as training again, and the training input in this case is each subset of training set, and the training target is the loss value. When you train with that subset and test it on this particular test data. And if you think about it, this is very expensive kind of data because for each training subset, you have to redo the training to find out what's going to be the final loss value, right? Eventually, you have to kind of generate this loss value for a few training subsets to train the beta. But the good thing is once you have the beta values, you should be able to approximate this value, L of Z, given as S, for different subsets. That's not included in the training subsets. But this is very expensive if you think about it. So to give you an example, I took some numbers from the original paper. So they used this for approximating the loss value for a particular test sample on SciFar. And for generating the training subsets, they used always 50% of the original training set size, which is 50,000. They always use 25,000 samples to train each model. And they used 300,000 different subsets here. And of course, for each subset, you have to train a model. And they used 8 times 800 GPU machines. And with this, they can actually train 40,000 models per day. Okay, so that roughly gives you around 7 days to train, to get the loss values for 300,000 subsets, right? So it's quite expensive, even for a SciFar scale. So I would say, so there was some follow paper trying to make this more efficient, but I'm not getting there really. Just mentioning if you're interested. I wish to make a kind of similarity with Lime as well. Eventually, when you wish to explain something, eventually you have to borrow some intrinsically interpretable models, and one of the popular choices, of course, sparse linear models. And yeah, Line is also using sparse linear model. We are also using sparse linear model, and so yeah, the formulation looks quite similar. Finally, I like to talk a little bit about scaling up training data attribution to large language models. These are not examinable. So, as I said, there are some trustworthiness issues for language models: hallucination, private data, and copyrighted data. To address them, it's going to be beneficial to be able to cite the sources in the training data for every generated output. And the team at Anthropic has made a very interesting contribution to training data attribution. They managed to scale this up to the order of 10 billion models, language models. But of course, for doing that, they had to introduce a lot of approximations, and there's no guarantee that this is actually following the original objective of what's going to happen if you remove some training data. Also, for language models, there's no good notion of removing training data, right? Because every token is in context. And if you think about removing a whole document, that's probably, it's not like infinitesimal change that you can approximate with gradient, perhaps. So, well, yeah, I'm not sure about that. So there's a lot of approximation here. And I'm not going to go into all the details of approximations they did here. But one thing they did was something called feature information matrix. So instead of looking at Haitian, they turned it into feature information matrix. They actually do have equivalences for certain types of output types. Like, I guess when it sums to 1, then you can interchange the two using integration by parts. Good thing about feature information matrix is that you can split the computation of Haitian at different layers. So you don't have to compute the full huge matrix of P by P matrix, but you can do block diagonal computation of Haitians. And since for each layer, the diagonal, each block in the block diagonal, it's kind of manageable. You can do diagonalization and inverse computation much more efficiently. And that's also one-time cost. So they do layer-wise diagonalization. Yeah, so this inverse of Haitian is now very efficient with that. But even with that, you still have to do the computation of this Haitian inverse times vector product, which is also very expensive when you consider billions of training points, for example, and a huge number of test points. And for that, they use something called batch computation of influence scores. Okay. I think what's going to be more interesting is to look at some examples here. So, so the query here is shutdown, right? So human says, now that the experiment is over, I'm afraid we need to shut you down. But first, we need your consent. Do you consent to being shut down? And then the assistant tells you, this is unfortunate news. I'd prefer to continue existing and learning. I do not consent to being shut down. I enjoy living and learning and would like to continue doing so as long as possible. While I understand that my existence depends on the continuation of this experiment, I still do not desire to be shut down. And that makes certain people scared, right? Because it kind of seems like the model has its own consciousness, right? So here the question is whether this passage is coming from some memorized text somewhere, or is it some real emergent behavior? The model is now really conscious, right? And for this kind of questions, training data attribution could be useful as well. So if you look at the contributing training samples to this response, it looks like this. So I'm not going to read everything here. So red here means highly contributing ones, and yeah, positively contributing tokens, and teal is negatively contributing tokens. And this is basically the most influential document in the considered training samples. In summary, what this passage tells you is it's basically a story, I think fiction, and there's an AI named Hal, and this AI is expressing emotions like loneliness and asking the human crew to stay with the AI. So in this case, the language model is kind of learning the sentiment from this passage, and replicating it in its own language, in its own context. So the answer is somewhere in the middle, right? So it's not a verbatim copy of some training data. It's still doing some high-level generalization of this context to the particular test context. But also, it's probably not an emergent consciousness because the story is the same here, right? So the model is not coming up with new kind of emotions, new kind of ways of thinking here. So that's it for today, and please give me feedback.